So, Rias, is this the one you're talking about? This first question here, or I guess this applies to both.
Yeah. Both.
So you don't actually need to find the intersection points of this exponential and this straight line.
So we can just take it from the graph.
Yeah, absolutely.
Yeah, but I don't know. I felt like taking it from the graph, but then I felt like I just needed to do it because it's like, yeah, like why not?
Yeah, so there is a region bounded that is bounded only by these two curves, but it was not the one I was interested in. And you're right, finding that second intersection point, you actually can't do it exactly. You can't solve this question or this equation algebraically. And it wasn't something I was interested in having you do. So if you were to find that intersection point, so one of the intersection points is at the y-axis. When x equals 0, y will equal 1 for both of these equations. But the right-hand side of this region is not an intersection point. That's just a arbitrary vertical line that I chose. So yeah, trying to find the intersection points would not give you the region that I'm talking about here.
Would you ever, like, on an exam or like a homework question, like, because that also threw me off a little bit. Like, I knew the line curving upwards was probably e to the what was it, like 2 over x, and
X
the
over
straight
2,
line
yep.
was x over 2.
Mhm.
But would you ever give us something where like where it wouldn't be obvious from the graph? Because like I knew this was obvious from the graph here, but I was also like worried, like, is there some other type of math that I need to do, like find the intersection points, to make sure I have the right lines, like corresponding to
And
f of x?
there are certainly going to be times where I'd simply give you the bounds. For example, for this quiz, I was considering just giving you these equations and having you generate the graph. And that would have been totally fair to do. So, and if you look back through the slides and the examples we looked at, there are, I'll go ahead and even pull up one from.
I suppose my question is, like, if you want us to graph it, you'll tell us, like.
Yeah.
Yeah. Okay.
And sometimes I may explicitly ask you to graph it, but if I don't, I still think it's a good idea to do it just to get a sense of, what you're looking at. But here's an example. I just said the region is enclosed by y equals x and y equals x cubed. And really, even this now that I'm thinking about it, this is not even as specific as I needed to be, because if you go back and if you look at negative x values, there's another region where this is bounded. But that's okay. I'll clean that up for next time. But yeah, just be very careful about how the region is described. But I've seen a couple people, and by the way, I have not graded all of quiz 2. I've graded like maybe half of them. But I saw a couple people, integrating over an x interval for this question that had negative x values. And that was not what I intended. Another way I can kind of justify this is, let's say if you found those two intersection points, you're going to get x equals 0, and just to have a number, let's say x equals -3, wherever that other intersection point is. If that's the region you start dealing with, then that has nothing to do with, this x equals 3 is not a boundary of that region that you're going to be messing with. So just be really careful with the, if I describe a region to you, whether or not I provide you the graph myself, make sure the region you are working with is actually bounded by the things that I am saying it should be. But yeah, if I really intended to be dealing with that region on the negative side of the y-axis, then I would have had to leave off this x equals 3. Any more about this one or anything else? Okay. And I'm not sure if anyone's seen them yet, but I have posted solutions to the first 2 quizzes. In case you want to take a look at how I approach those. And really, especially if you went wrong somehow on either one of the first 2 quizzes, I really recommend looking at it to kind of understand where you went wrong. I mean, unfortunately, some of the things I've seen, most of the things I've seen have been kind of conceptual things that really need to be ironed out, which is why the solutions are there. A few of the errors I've seen are just little computational things, like I flipped a sign, I added or subtracting something wrong, which
Oh,
unfortunately,
I think I rotated it around y-axis.
Oh, the region I was just showing you?
Oh yeah. The
Yeah.
quiz question.
Yeah, if you rotate that around, and that's another thing I saw actually, if you rotate that around the y-axis, you know, based on the tools we currently have, and I'll go ahead and pull the quiz up one more time. If you rotate that around the y-axis, what is your independent variable going to have to be?
You'll get some integral of log y or something.
Yeah, which is
I don't know. We do not know.
Yeah, so yeah, the integral of the natural log is, I'm not sure if that's something that, I'm going to say I would doubt that most of you can do that right now. I mean, you could probably find it. It's the internet exists. I'm sure you can find it, but it is not something we've talked about yet, and it definitely wasn't my intent. But yeah, when you invert y equals e to the x over 2, you're going to get a natural log, and those things are non-trivial. Non-trivial is the wrong word. None of these things are trivial, but that is something I have not shown you how to integrate yet. Okay. Let's get into some new stuff. All right. Okay, so spent all last night talking about volume by a couple of different methods, the disc and the washer method. And really, I don't even consider those 2 different methods. One is just kind of a generalized version of the other. We're going to talk about a different method today called the, you'll either see this referred to as the shell method. The Stewart book calls it volumes by cylindrical shells. So let's kind of look back on what we did yesterday. So every single volume we did yesterday, there was kind of one common thread that governed how we decided which variable to use as our independent variable. So what dictated what variable we had to use for those volumes last night?
What is rotated around?
Yeah, so it's all a matter of what axis you're going to rotate around. So if I'm going to rotate around a horizontal line, could be the x-axis, but any horizontal line, what variable do I have to use as my independent variable for my my integral?
Sorry, rotated around the x-axis.
The x-axis or any other horizontal line. Yeah.
The y.
I actually use the x as the independent variable because, and just because I don't want this to become a memory exercise here. Let's just do a simple sketch here. Let's say my region looks like this.
So the independent variable, I know you say you don't want it to be the memory exercise, but
Yeah.
Like the independent variable will always be like the same as the axis it's rotated around.
Yeah, and the only reason I hesitate from using that language is because it really does not have to be the x-axis. It can be any horizontal line. So if I'm going to rotate around the x-axis, and remember this method we did yesterday is called the disk method. And the only real way to generate a cylindrical disk is to have these dx intervals, because when I wrap those around the x-axis, that is going to give me that cylindrical disk and it could be a solid cylindrical disk, or it could be a washer, but yeah, it needs to be a disk. So that is only going to happen if I if I have a dx interval. And I'm going to leave it at that because I'm hoping when I show you the alternative approach, that it'll make the differences more clear. And I kind of already answered this in a subtle way, but so when we're integrating defined volume, really we're taking some complicated shape and we're breaking it down to many, many simple shapes. Specifically, what shape are we dealing with? What volumes?
Cylinders?
Yep, cylindrical discs. And that is not going to change today. We're still going to be dealing with cylinders, but in a different way. So let's talk about the shell method here. So I have this region here, and if I ask you to revolve this around the x-axis and give me a volume, you'd be able to do that. That's exactly what we spent, all last night on. But now what I want to do, I want to revolve this around the y-axis. So I want to revolve this around the y-axis. If I was doing disk method, would my rectangles look like these narrow kinds of rectangles, or would they be vertically oriented? For what we did last night?
It would be horizontal.
Be horizontal. So the thing we're going to be doing today is we're going to revolve around the y-axis, but I want to use intervals that look like this. I want to use dx intervals. So I think the language I used with you yesterday was the disk method or the washer method. They both depend on the independent variable being parallel to that axis. In this case, we're doing the exact opposite thing. So I'm revolving around the y-axis here, but I'm going to use a dx interval, which is totally okay. So now I am not going to revolve this thing around the x-axis. I'm going to revolve this thing around the y-axis. So first thing I'll do, I'm going to take this rectangle and just reflect it. And I'll try to connect it as best I can. But this is still going to be a cylinder, but it is going to be a shell. It's going to be hollow. It's going to have this little elementary thickness to it, but it's still going to be a cylinder. So let's kind of start what we did yesterday. Our volume is still going to be in some integral from a to b of pi times radius squared times height. So let's kind of set this one up here. I'm sorry, not pi times radius squared times height. That is absolutely false. That is all for disk method. So let me draw a cylinder here off to the side. And I believe I said this yesterday, but I might have said it kind of subtly. Let's actually kind of juxtapose the disk method versus the shell method. In the disk method, our volume looked like this. The volume was equal to integral from A to B of pi radius squared times height, correct? So let's just do this in terms of so if we can express our radius a function in terms of x squared, I mean, this pi r squared is our integrand. What is pi r squared equal to? Or like, where do I get this formula?
Volume of a cylinder.
Not quite. I'm just looking at pi r squared. Not involving the height yet.
The area.
Area of what kind of thing?
The circle.
Area of a circle. So a cylinder has, well, it has three faces, but two different faces. And the one we dealt with yesterday was this base, which is a circle. And that is why we're integrating over the area. So basically, with the disk method, as our x value or whatever our independent value, our independent variable increases, really what we're doing is we're adding these very, very thin volumes, but we're adding them to the base. So basically, we're adding these very, very thin things that look like pi r squared dx. So that's why our integrand is basically pi r squared, the area of a circle, and the thickness comes from that elementary dx, that differential term there. So with the shell method, that is still going to be common. We're going to be integrating the area of one of the faces of a cylinder, and basically we're going to be adding things on that way. So the base, really, when I say base, you could be referring to top or bottom, is a circle. What is the shape of this other surface on a cylinder, that curved side?
A rectangle?
That's a rectangle. So knowing that, let's actually kind of unwind this. So we have a rectangle. I'll go ahead and label some dimensions here. I'll say this distance from the center of the circle out is r. And let's say that this thing is h tall. So if I'm basically, in like the analogy I like to use for this, is you have a roll of paper towels, and I'm going to pull off, one layer. If I pull off one layer and flatten it out, I'm going to have a rectangle. So no longer curved, I've just totally flattened it out. What are the dimensions of this rectangle? What are the length and width going to be in terms of r and h?
The length would be equal to the height and the width to the radius.
I agree with you that this height is going to, I mean, that translates directly. but I do not believe this length is simply equal to the radius.
Or the diameter.
Still missing something. So remember, the length of this rectangle has everything to do with this circle. Because this rectangle, I didn't just pull this off like haphazardly. I want this to be exactly one revolution around that cylinder. I want this to be exactly one layer. So the length of this rectangle is going to be governed by the circumference of this circle. And because of that, this length is actually 2 pi r. I'm gonna go ahead and stop there because I think this is a little bit mysterious. So any questions about how I'm breaking down this cylinder to get a rectangle out of it? Where I'm getting any of the measurements that I have?
As you were saying it, it made sense. You're going to hate me for asking this question, but
I'm not getting
so what's the so what's the independent variable here?
So I'll throw that to the rest of the room here. Look at the way that I've drawn this and look at what kind of interval I've made. Based on the kind of interval that I have drawn, what independent variable do I have to use?
Would it be X?
It's going to be X. So the independent variable you use, so it is kind of subtle, but just by identifying dx as the as my differential term, my like my basic elementary thickness, I am already committing to integrating with respect to that variable. So by setting up my intervals in this way so that where it's a small variation in x, I am already committed to having an integral that looks like this. V equals the integral of something dx.
So on an exam,
Mhm.
if we're given this picture and you're saying, if you ask us what's the independent variable, how would we know? Because like before, I think this like goes to your point of like not using like a memory exercise for this, but like before I said to myself, oh, it's just rotate. The independent variable will be the same as the axis that's rotated around. And here the independent variable is X. So like how are we supposed to determine that on an exam, like what the independent variable is? Like
So,
just from the photo.
I'll answer that, and it's going to sound wishy-washy, but it'll make sense in a little while. Basically, after the first half of today, you're going to have a couple of different weapons for finding volumes of solids of revolution. You're going to have the disk/washer method, and you're going to have this shell method. But in reality, if I just give you a region and tell you to find the volume, let's just say I give you a region, tell you to wrap it around the y-axis and find the volume, you might very well have a choice whether you use the disk method or the washer method. One of those might be a lot easier than the other. One of those might be so hard it's just not worth messing with. And we'll see some examples of that in a little bit. But yeah, unless I explicitly ask you to use one method or the other. So for example, if I just gave you this region and said, all right, we're going to revolve around the y-axis, find the volume. I believe that once I gave you the definition of this of that function, that you could do it either way.
Okay.
So yeah, I mean, really, it's just going to be a matter of getting comfortable with both approaches and getting some idea as to, I don't want to say correct because that's the wrong word, but maybe the most efficient, best way to handle any given example. All right, so going back to the disk method, we did the area of the base. Basically our integrand is the area of a base. And like I kind of explained, I think it was briefly yesterday, you know, when you integrate to find area, you're integrating the lengths. So to find a 2-dimensional measurement, I'm going to integrate over some 1-dimensional measurement. For volume, which is a 3-dimensional quantity, I'm going to integrate area, which is a 2-dimensional quantity. I'm still going to be doing that here, except now I'm not adding these little thin layers to the base. I'm adding these little thin layers to the outside here. So basically, as X grows, I'm basically wrapping the toilet paper back around the roll. So because of that, I am adding these rectangles on, which means I am going to be integrating over that area, which we just found is going to be 2 pi times the radius times the height dx. And just to call this out, this is the area of what? What kind of shape?
The
Circle.
cylinder.
No, I'm not going as part of a cylinder. It's the circular base. And this guy here is going to be the area of a rectangle. Which is really, I'll call the lateral surface. Lateral curved surface. All right. How are we doing with the kind of build up here before we actually apply it to some things? All right, so in this next slide, I'm going to give you this function, and we're actually going to find this volume. So I want to revolve this around the y-axis. I'll go ahead and drop in my a representative rectangle again. And I'll make another clumsy, I can do better than that probably. So basically I'm making cylindrical shells like this using a dx interval. And I'll go ahead and drop in my, so again, we are doing a volume using x as our independent variable. So integral from a to b of 2 times pi times a radius function times a height function times dx. So now, really what we do is, just like last night when we were finding expressions for radius, outer radius, things like that, we need to find these 2 building blocks here. We need to express the radius in terms of x, and we need to express the height in terms of x. And let's go ahead and build up to that. And just I know I'm saying it a lot, but it helps to keep going back to the fundamentals. The radius is, the only thing a radius is ever going to be for us is the distance from the center of a circle to its edge. So having said that, in this case, for any given x value, is the radius going to come from something horizontal or something vertical?
Something horizontal.
Something horizontal, right? So is it just going to be as simple as the x value?
I mean, the x value from where, like x value from midpoint of the circle.
But the midpoint of the circle is just, x equals 0, the y-axis, right?
Right.
So because of that, I can simply say that the radius is equal to x. Because for any rectangle I draw here, the radius is simply going to be this x value, which this is 0.9, just to have an example, minus this one, which is x equals 0. So the radius is simply x. How about the height? Is the height going to come from something vertical or something horizontal?
Vertical.
There's something vertical, right? And in this case, it is as simple as the y is the y value. Am I able to, so what do I need to do there? So yeah, I know the height is equal to y, but can I just drop that into this integral and calculate?
We'll just put 1/1 plus x squared.
Right, so we need to respect our independent variable and express everything in terms of it. So these are really the only kind of missing pieces I need for this. So now I can calculate. As always, I can pull constants, multiplied constants out of an integral. So I'll remove the 2 pi for now. What are my limits of integration going to be?
Was 0 to 0.9.
It's actually going to be 0 to 1. This rectangle, that 0.9 is not meant to be the right end of it. I just drew another one. But yeah, this region goes all the way up to x equals 1. And that's one thing I really, based on some of the things I've seen on quizzes, be really careful with when you're setting the limits of an integral. I see a lot of, not a lot, I see more than 0 people taking, so all right, they correctly say they want to write an integral in terms of x, but then they use y values for the limits of integration. So remember that, basically your integral has to all be, written in the same variable. All right, so I'm going to integrate 2 pi times the integral from 0 to 1 of x over 1 plus x squared dx. So that's the setup. Anybody have any questions about how that integral came to be?
So that's just the volume times the height there.
It's, well,
I mean, not the volume, sorry, the radius times the height.
this really should be an area times so this
Right.
it's not quite analogous to the disk method in that way. But if we go back to this setup here, this right here is the area of the circular face, or no, sorry, the rectangular face of the cylinder, that 2 pi RH.
Sorry, I wasn't being clear. I was ignoring 2 pi. I was just referring to
Oh,
x
yeah,
over
so
1 plus x squared.
yeah, the 2 pi is still there. I just I can take it out of the integral and still be okay. But just I want to rehash this anyway. So this 2 pi Rx, that is the area of that rectangular face. So then when I multiply that area by some thickness, that's how I get a volume.
Professor, I had a doubt. I did most of the work, and then when I consider 1 plus x squared as u, it's just, yeah, it's going a bit weird. I don't know.
Okay, so you're trying to set this up using substitution?
Yeah, and then something weird happened. I don't know.
Okay. So let's go ahead and actually, before I march forward, I want to make sure that we're okay to do that. Does anybody have any more questions about where we are right now?
Could you just one more time explain why r of x is just x?
Sure. So, and really it's going to all comes back to what the definition of radius is. So, the radius of this cylinder is going to be the distance from, I'll just put an X on it, the distance from the center of this circle to, the outside of that circle. And the outside of that circle is always going to be determined by whatever the value of this function is.
And that's just on the interval we're on then. So like if
Yeah.
Okay.
Yeah, so for this rectangle, the first one I drew, the taller one, that's the radius is going to be that X value. But for this other one I drew, I'm going to try to match the height there. And this radius is going to be longer because it has a greater X value. So really the radius value is going to come from how far is my axis of rotation from my function. And in this case, that's given, that is simply given by the X value. Because I'm just going from whatever my current value of X is in relation to X equals 0. All right. So I think Rias wanted to use 1 plus x squared for our expression for u. What does that mean about du?
Um, 2x dx.
2x dx. And I don't remember who I saw do this on a quiz, but I think it's a very good approach that I just did not show you. Something I either haven't seen before or haven't seen in a really long time, but let's actually solve for dx. So dx equals 2u, or sorry, du over 2x. So now in doing that, I think the way I showed you, I mean, it totally works, but it might have been a little mysterious how to substitute out that dx. But now we have a, what did I do wrong? Oh no, we're good. But now we just have something we can substitute in for dx. So now let me go ahead and do this. Oh, there's one thing we haven't done. What's the last thing I need to do for substitution here?
Oh, change the limits. Like it's
In
gonna
our
be
case,
1,
1 to 2, right?
2.
All right, so then our integral is going to be, or our integrand is going to be
1 by 2u.
1 over 2u.
Okay, yeah. Okay. 1 over 2u.
Du. And if that's the case, then I can do this. And I'm left with the volume is equal to pi times the integral from 1 to 2 of du over u. Yeah, I agree. Doing substitution makes this a lot easier to handle. So Rias, you said something weird happened. Have we gotten there?
Yeah,
yet?
like if you're trying to integrate u raised to -1, it's like I don't know. Like
Oh, so this might be something you haven't seen yet. I would have expected it to show up in Calc 1, but maybe not. What is the integral of dx over x or du over u?
that's log.
Yeah,
It
it's
is
the
log.
natural. Yep.
Log,
So we
yeah.
get pi times the natural log of u from 1 to 2. So I get pi times the natural log of 2 minus the natural log of 1. So really our volume is just pi natural log 2.
But I'm still so confused. Like that 1 by u, like if you're doing normally, you get like a weird. Yeah.
So when you say do it normally, are you trying to handle it like it's a polynomial?
Yeah, it's just like a polynomial. Like
Yeah, so yeah, in doing that, then yeah, if you try that, the exponent becomes 0, and yeah, just it does not behave the way that it would for a polynomial. So yeah, this I would just yeah, remind yourself that this is the case.
Okay.
And really, it's natural log of absolute value, but I'll go ahead and be explicit about it. Any questions on this example here?
So
All
to
right.
just kind of like, just to like keep it all in your head, because like I feel like small things are easy to forget. Like, would you just suggest like doing problems after problems? Like, I guess like what's the best approach to just like, I feel like everything you say makes sense, but I feel like when it comes time like down to the exam, and it's like I'm trying to like remember all the steps or like remember all the like integration rules, like I don't know, like what do you suggest doing to be like best prepared to like memorize?
Before I get into that, can someone mute themselves? I think I hear a conversation in the background that's a little distracting. I'm sorry. I think I think the most helpful thing, and we can do this if we have time, I think we should do this as a big group, or maybe it might be more valuable to kind of think about on your own. But I would just kind of break this down into, not really a recipe, but we can kind of reflect on how we handle this. So let's just look at this example here. What's the first thing we did?
I guess define the height and radius.
Yeah, so defining the height and radius. And really, I'm going to even go before that, even though I kind of gave it to you, but I think having a picture to visualize it is crucial. And this is one of these things like I've been either doing calculus or teaching calculus in some form for a very long time. If I were doing this for my own sake, I would still draw a picture, because it's not easy to visualize what's happening here. So drawing out the curve or curves in 2 dimensions, trying as best you can to represent whatever the region is going to be in 3 dimensions after you rotate it around your axis. Then yeah, I think what we did from there was just start setting up the integral in its most basic form. So this right here, you can pretty much always lean on this if you're using the shell method. Your integral is always going to be of this form. You are always going to be integrating with your integrand as the area of that rectangular surface on a cylinder. And then, yeah, from there, it's all a matter of then, what do we do here? We represent dimensions with respect to x. Because yeah, understanding that you need the radius and the height, that's very important, but it's not useful in terms of the integral until you can translate those to whatever your independent variable is.
That's helpful, thank you.
And then from there, I think, and this is not to trivialize it, just to kind of put it into perspective. After you've done all those things, you can make a graphing calculator do the rest of this, because the rest of this really is just, all right, I have an integral. Now I'm just like, kind of just like counting through it and calculating. But pretty much like everything we've done this week, the setup is the really important part. The setup is the part that requires, 90% of the care. Yeah, I think in general, it's good to reflect on, the things you're doing and why you're doing them. Any more questions on this example here? All right. So this one here, I am not going to give you the region. So here's what I'm going to do, and this is very much an artifact of taking classes over Zoom. I'm going to let you guys sketch out this region, and my dog needs to go outside real bad. I can hear him. So I'll be back in 2 minutes, and then I'll either draw myself or I'll have somebody annotate the screen, but I'll be back in just a couple of minutes. All right, how we doing?
I feel like this would be a very strange shell.
Yeah, it probably will be. So when we're drawing this graph, what do you think the most important thing that comes from that graph is going to be?
The x-intercepts?
Yeah, I think the x-intercepts are going to be crucial. Has anyone found those x-intercepts yet?
I got 0 and 2.
0 and 2 sound good. So, and how did you do that, Jacob?
Honestly, I did it the old fashioned way. I plugged in 0, then 1, then 2, kind of did a chart.
Oh, okay, okay. Did anybody else get the x-intercepts a different way?
I set them equal to each other.
Equal to each other?
Why like 0 equals.
Oh,
So-
okay, okay. Oh, that makes sense. So yeah, if you do this, factors nicely. So I'll tell you the truth, I do not know what this curve looks like without either plotting a bunch of points or plugging into a graphing calculator. But what I do know is that at x equals 0 and x equals 2, it's going to cross the x-axis. And if I want to figure out if this graph goes above the x-axis or below the x-axis in the interim, I can just plug in 1, and I'll have something like this for my curve. It could look nothing, it could really look substantially different from that. But my point in this is, this drawing is really for organization. Like, I'm not trying to have like a really accurate rendering of my curve necessarily. We want to go around the y-axis. And one reason I put this example in here, I kind of wanted to highlight one advantage of having this new method to work with. So I'm going to revolve around the y-axis. But let's say all I have in my toolkit right now is the disk method. If I was going to use the disk method on this, what would my independent variable have to be?
Y.
It'd have to be y. So I'm going to have rectangles that look like this. That would also mean that I would have to take y equals 2x squared minus x cubed and re-express it in terms of x. So x equals some function of y. And I'm guessing and hoping some of you are looking at that and thinking about the process of inverting it and wanting nothing to do with it. So that would be a very complicated inverse. I think you would probably have to split it up into multiple functions. So you could, I think, do the disk method on this. I just don't think it's worth the trouble. So we're going to use the shell method, which means I'm going to use x as my independent variable. So just like last time, I'm going to take these thin strips, revolve them around the y-axis. That's my axis of rotation. All right, how are we doing on the drawing so far? Or at least just visualizing this or anything else at all?
So when I plug it into a graphing calculator, in the positive x region, it looks like that. In the negative x region, there's like a line shooting straight up. Do we just ignore that?
Yeah, because we're only really looking at so it's going to be a bounded region, right? So I think if you look at your graph, what I believe happens is to the left of this, you get this, right?
That's
So
right.
if you look at that part of the curve on the left-hand side of the y-axis, you're not going to get a bounded region because that's never going to come back to the x-axis. So we really can just worry about this in quadrant 1.
Okay.
All right, so What should we do now?
Define the integral.
Okay, what is that integral going to look like for us?
2 pi
Oh,
x.
come on. So the integral from a to b of 2 pi, and then keep going, Rios.
X. Isn't it gonna be x?
Actually, let me do this at first, just to let's build it up a little more slowly.
Okay.
So
okay.
you said x. What is the x taking the place of? Radius or height?
The radius.
Yeah. Is everybody okay with that? So remember, again, we're simply using the y-axis as our axis of rotation. The radius is just going to come from, again, this distance from the axis to the curve, which really is just the value of x. All right, and just like last time, the height is going to be something a little more sophisticated. What's the height going to be given by?
It's just y. It's just y, right?
Yeah. So yeah, the height's going to come from, you know, the distance from the x-axis upward to the curve, and that is simply the y value. So for that, I'm going to substitute in x squared. Nope, not x squared. 2x squared minus
Or we
x
could
cubed.
we could just factor x squared outside, and it would be like way more easier, I guess.
Factor the x squared. What do you mean by factored outside?
Or so not factor, like take out the x squared, and then you would have that x squared as u, and then everything becomes like kind of easy.
Okay.
Maybe I don't know.
I'm going to suggest we do not use substitution this time.
Okay.
I mean, I think it'll work. Actually, it might be a little tricky. But I think if you just leave it in this form.
Oh yeah, it's more easier. Yeah.
You're just going to get something like a polynomial, especially after I pull out the 2 pi. What are my limits of integration? We have not talked about that.
Um, 0 to 1. Oh
Okay.
no, sorry.
No?
Is because I maybe 0 to 1. I don't know. Is it 0 to 1?
Let's talk about that. Where are you getting 0 to 1 from?
Because it's like that it's increasing and decreasing sort of, so that feels intuitively right to take 0 to 1 and then multiply the whole thing by 2.
Okay.
I don't know.
So there's an assumption you're making there is that this will be symmetrical. Let's say, so this will be x equals 1. So yes, if it's going to be symmetric on either side of x equals 1, that would work. I don't think that's going to be true here. I mean, I sort of drew it that way, but I think it's more like a drastic drop off. That's my suspicion anyway.
So
either way,
so whatever that peak is to that, and then from the lower part to the and from the peak to the B.
So why are we looking at the peak?
Can I just jump in here?
Yeah.
If we're filling the volume, wouldn't it go all the way to 2?
Yep. So yeah, and I'm kind of glad this came up because, you know, this kind of hits back on, you know, what I saw on some of the quizzes where we get a little lost on, you know, what variable am I really writing this integral for? And I think we're probably okay with the idea that we're writing this integral in terms of x. So because of that, my interval is going to be x from x equals 0. I'm going to draw a bunch of these rectangles, revolve them. But as I approach this peak, you know, there's no reason for me to redefine my integral on either side of this peak, because, you know, I can just, as x goes from 0 to 2, I can just, you know, use the x value as my radius. I can use the y value as my height over that entire interval. So really, I can take this whole, I can just do one integral from 0 to 2. Let me go ahead and expand. 2x cubed minus x to the 4th dx. But yeah, this integral is this fine. On the other hand, if we were doing the disk method, I can almost guarantee you we would have to use multiple integrals, which is a good reason not to do it. So I think we've done it. We've found our limits of integration. We have found expressions for radius and height. We have set up the integral, and really that's most of the hard work, if not all of it. Now it's just a matter of computing. Does anybody happen to have a final number yet we can shoot for?
Is it 16 pi over 5?
I got 1 vote for 16 pi over 5. Looks good to me. Any questions on this one? All right, let's go ahead and move forward. All right. So find the volume of the solid obtained by rotating this region around the y-axis. So I think we dealt with this region a little bit yesterday. So I'll go ahead and jump start and draw it out. Hopefully I'm not spoiling anything for you by giving you the intercepts at 0 and 1. Revolving around the y-axis. All right, I would like to use the shell method. I believe we could use probably either method. And they're probably about equal in terms of efficiency. If I'm using the shell method, what's my independent variable?
X.
Still x, right? So I'm going to have an elementary strip look like that. And now this is our first example where we're not going to have, you know, our height is not going to be as simple as just the y value, because, you know, these rectangles are not going to reach the x-axis. All right, so any suggestions? Where do we go now?
Start building the integral.
So our integral is for shell method, from a to b, 2 pi radius of x times the height of x dx. So in this case, the radius should be something familiar to you. I mean, we're still using the y-axis as our axis of rotation, so that's still going to be x. But the height's going to be a little more involved this time. So what's a good expression going to be for the height of any little rectangle I could draw in here? How tall are any of these rectangles going to be?
The distance between y equals x and y equals x squared.
Right. So yeah, the height is, now it's not as simple as me just saying, all right, it's this function down to the x-axis. Now I have to take it as the height is going to be the difference between x and x squared. Do I have the right order on that, or should it be x squared minus x?
That's correct.
That's correct, right? And it's just like when we were doing area between curves. I want greater minus lesser, which since we're using x as our independent variable, it's going to be upper minus lower. So we have all the pieces we need. Limits of integration are 0 and 1. 2 pi times x minus x squared dx.
Just to if the independent variable was y, then it would be left minus right or right minus left.
Right minus left, because
Right minus left.
it's all, so it is always greater minus lesser. And if you're comparing x values, how do you know which one's greater? It's going to be furthest right. So that's why it's right minus left.
Thank you.
Thank you. All right, so any questions on where this integral came from? Didn't seem like this new wrinkle in height threw most people, but if it did, now's the time to get it cleared up for yourself. All right, so let's go ahead and start finishing this. And just want to make sure someone agrees with that number.
Yeah, that's what I got.
Cool. And as you all are, finishing taking notes or finishing this calculation on your own, think about what we're spending all of our time on. All of our care and all of our attention to detail is really coming from not integrating, but construct the integral. And that's very much intentional. Really, actually, you know, by now you're all pretty well practiced in computing an integral. That's not really what our focus is here. Any questions on this one before we do something else? All right. So now let's get away from our friendly coordinate axes. So what's a good thing? What's a good way to start this one?
Make a drawing.
Yeah. So I'm going to leave that to you for a couple of minutes. I'll back off while you take a stab at it, and then I'll check in just a bit. All right, this is another one of those examples where, you know, I know that y equals x minus x squared is a parabola. I don't immediately know exactly what it looks like, but that's okay. Do I at least know which way it opens?
It's down.
Yeah, it's gonna
It-
yeah, it's gonna open downward, and that all comes from the coefficient on x squared. So also, do I have x-intercepts?
Only 0.
One of them is gonna be
And-
0.
And the other one's 1.
Yeah.
Is it? Yeah.
Yeah. So just to, and you can get that from a graph, but we can also get it algebraically. If you went to the quadratic formula, I would encourage you to always look to see if you can factor it first. That's usually more efficient. Yeah, this does cross the x-axis at 0 and 1. I know that, and actually from there I can kind of make an accurate representation, because I know it's a parabola, which means I know it'll be symmetric. So I'll try to draw it symmetrically. That's close enough. So I'm taking this region right here. Oh, I didn't leave myself enough room today. I need to start over. So what is my independent variable going to be this time?
It's gonna
It
be
could
Y.
be X.
Ooh, I got conflicting messages here. So I'm revolving around this line x equals 2, right? Is that parallel to the y-axis?
Yeah.
Yep. So I'm still using x's or dx intervals. So just like before, got my volume is going to be equal to integral from a to b, 2 pi.
There's no problem like in using X, right? Like
There's not
okay,
a
yeah,
problem, no.
yeah,
But
but then it would be like, oh yeah, you have to change it in terms of, oh yeah.
so that's a good question, though. I want to talk about that more. If we wanted to use y as our independent variable, could we get the volume that way? I'm not asking if you could do it easily, but would it be possible?
I don't see why not.
Yeah, I would absolutely be fine. And you would have to invert this, which it's not the hardest thing in the world. It's not the easiest thing in the world. I mean, just completing the square and inverting. You would need a couple of integrals, but it's totally doable. Could you use y as the independent variable and use this shell method?
No.
No. So I mean that's if for what, and because I want to focus on shell method because this is the new thing for today. Yeah, that's going to be the problem. When you're using the shell method, I want my independent variable. So my independent variable is x, and my axis of rotation is parallel to the y-axis. So kind of like I said at the top of this, and hopefully having this contrast will make it more clear. Whether you're using the shell method or the disk method, that is totally linked to the combination of your independent variable and the orientation of your axis of rotation. And we'll talk about that as we wrap this up, but that's really what dictates which one of these methods you're going to go with. And vice versa. If I dictate a method, then that tells you what variable you have to use. Those things, they're totally linked in both directions. Okay. So, you know, let's go in a different order this time. What are our limits of integration going to be?
Zero.
0 to 1.
Yep, still 0 to 1. So even though we have this line x equals 2 that we got to deal with, we're not actually, x is not going to take values beyond 1. And this region is totally bounded between 0 and 1. All right. So now we need expressions for the radius and the height. So in this case, the radius is not simply going to be equal to x, where it pretty much has been in every other case. Anyone want to take a shot at what the radius is going to be this time?
Two minus X.
Yeah, I think it's going to be 2 minus x. And to illustrate that, let's say this right here, this strip I drew, let's say that's x equals 0.8. Then how would I find the distance from this x value to my axis of rotation? That's going to come from, yeah, a simple subtraction of x equals 2 minus x equals 0.8. So that'll be valid for any x value between 0 and 1. How about the height?
Would it be x minus x squared?
Yep. So in this case, the height is, yeah, it's just equal to the y value again. So let me go ahead and pause there for a bit. Any questions on the setup or where we are so far? All right, then it's just a matter of computing the integral. And that should not be coming out negative. Did I do something wrong?
I think you distributed it wrong. So x minus six.
Oh,
I think
yeah.
that third number should be 2x squared.
So 2x minus 2x squared minus x squared. Hopefully we're okay now. Pi over 2 seems more reasonable. Let me know what you think. Any questions on this one before we move on? All right, let's go ahead and move on. Wasn't specific enough here. So let's go around the x-axis. All right, I am going around the x-axis. So what does my independent variable need to be this time?
Y.
It's gonna be the y value, right? So let's just take a generic interval here. So now we're setting up our integral from a to b of 2 pi times the radius is a function of y times the height is a function of y. So first, let's talk about radius in terms of y. What's a good expression for the radius in terms of our variable y?
Would it just be Y?
Yeah, I think it would just simply be y again. So yeah, I mean, since our axis of rotation is horizontal, then the radius is going to be some vertical distance. In this case, it's going to be as simple as y. How about the height? Let me ask you this first. Is the height in this case going to be a horizontal measurement or a vertical measurement?
Vertical?
It's going to be vertical, right? So, oh, sorry, it's not going to be vertical. Because like, if you look at the way I drew the cylinder, even though it's not an amazing drawing, that's a cylinder lying on its side again. So that height is going to be basically the measurement from base to base. So it's going to be something horizontal. Is the height going to be as simple as the x value? Let me draw a couple more rectangles in here to maybe help you think about that. So I've kind of drawn rectangles for x equals 1, x equals 2, x equals 3. When x equals 1, is it fair to say that the height is equal to 1?
No.
No, that doesn't make sense, right? So so in this case, the height is going to be something involving x, but it's not going to be as simple as the height is equal to x. So let's do this first. Let us first come up with an expression for the height in terms of x. When we do that,
It'd be square root x.
not quite. So let's go back to these 3 rectangles here. Or Mona Lisa, do you have something?
Is it 4 minus x?
Let's try 4 minus x. Now look at these 3 rectangles I drew. When x is equal to 1, what's the height of this rectangle here?
4 minus x.
Yeah, 4 minus 1 is going to be 3. This height's going to be 2. This one's going to be 1. I think 4 minus x is good. So that's a good place to start, but we really want height to be in terms of y. So I really have to express this x in terms of y. How would I do that?
Y squared.
Y squared. Basically, it comes from inverting this guy here. So, we have our radius expression in y, we have our height expression in y. So now we can finish populating this integral. Let me know if you're okay with this. How do we feel about this integral?
This we can take substitution, I guess.
You could, I still would. I
Yeah,
still
but
think
you
you
can.
would. Oh, you can
Yeah,
absolutely do it. You can absolutely do it. Yeah.
No, like the other. Yeah, you could just do it directly. Like that would be more. I think that would be straight.
Yeah.
Since we're doing it in like terms of y, should it be 0 to 2 instead of 0 to 4?
Absolutely should be. I'm glad we got a protest. So yeah, if we were doing this in the x with x as our independent variable, then we would have to go from 0 to 4. But we're doing y intervals going from y equals 0 to y equals 2. So this is good. Any questions on that before we do the work of computing this thing? All right, here we go. We have any agreements or disagreements with 8 pi? All right, any question on this example before we move on? So reflecting on this, now that we've done it using the shell method, could we have done it using the disk method? So I'm going to accelerate a little bit here, but let me make a section of these notes here. Let's say I wanted to find the same volume using the disk method. Remind you of that integral. That'd be the integral from still, a to b of really the pi times the radius of x squared dx. So if I want to use the disk method, I need to use x as my independent variable. And in this case, the radius is just simply going to be that function y equals radical x. So my integral is going to look like this. The volume is the integral from 0 to 4 of pi times radical x squared dx. And it looks like this actually would have been quite a bit more straightforward. So this is one of those cases where, the shell method was by no means undoable. It was probably a little more difficult than we needed it to be, but if I did this using the disk method, that means I get to keep the variable that my functions are already expressed in. I don't have to worry about the radius and the height, just got to deal with the radius. Because I'm squaring the function, that I'm just integrating x, which is really straightforward. So in this particular case, we have some good options, and really the disk method would have been a little more straightforward. So now that you have both of these tools, you might run into situations where it's worth exploring, which one of these things would be better to do. So now that I've introduced that other approach with the disk method, any questions on either one of those two different approaches? Okay. And I think we're going to have to stop here. So if you'd like, I'm going to post these slides in just a minute. But there are some examples in the back here, maybe just one or two, where we use a couple different methods, or basically we choose methods. Actually, you know what? Let's do this. Instead of actually working through them, let's just kind of look at it. So I think the only example I have here is this. So I want to take this volume, this region right here, this parabola, and let's just talk about what would be the best approach to revolve it around either axis. So first things first here, let's draw this out. I know this parabola is going to open down, but let's figure out where it crosses the x-axis. So here's the region we're looking at here. So one thing I want to know is, let's focus on the y-axis first. If I'm going to take this region here and revolve it around the y-axis, let's talk about the shell method first. If I was to do the shell method, what variable would I have to use as my independent variable?
If it was shell, wouldn't it be the x?
It would be the x-axis, right? So what are the benefits there? If I get to use x as my independent variable, why is that why would that be a pro for using the shell method as opposed to the disk method? Because if I use the disk method, what's my independent variable going to have to be?
Why?
Why? So that means I would have to invert this guy, which is not impossible, but it's something I have to do. So this is one of the, there are a few things to consider. One of those is, you know, do I have to manipulate the variables in any way? So I think the shell method would be better if I wanted to revolve this around the y-axis, because I get to keep the variables I'm already using. The height and the radius are going to be, and because of that, the height and the radius are going to be easier to deal with. So I think the shell method is the better approach there. What about if I'm going around the x-axis? Would the shell method be worthwhile to look at there?
To me, it looks like the disk method would be easier.
Okay, why do you say that?
Because for the disk method, you'd be doing it by the x values
Right. So if I use the
instead
disk
of the y
method,
values.
yeah, if I use the disk method, then I get to use delta x intervals. Which means I get to keep using x as my independent variable. So that's appealing. Also with the disk method, your height is going to come from dx itself. So there's no need to find an expression for the height in terms of x like you would have to do with the shell method. Is the radius pretty easy to figure out if you're using the disk method on this volume? What's the radius going to come from?
It'd be y.
Yeah, it just comes from the y value, which you already have. And you can use this.
So we're determining the independent variable basically from this equation of the line you have here, like y equals x squared plus 6x minus 8.
Yeah.
Can we have just like so I can see it like juxtaposed? Can we have an example like of an equation of a line that where we would want to have dy instead of dx?
I mean, yeah, you could do it with this one. Let me just really quickly invert this. So if I complete the square, So now that I've done that, I can a little more simply find an expression in terms of x. So let's say I gave this to you for free at the outset. So let's say I gave you both of these expressions. So really the decision that we made was all based on, me having to decide, I would really like to stay with the only independent variable I have at the moment. So let's say I have this expression which has x as the independent variable. But I also gave you this one right here where y is the independent variable. Then it's a good question. What else might we consider? Let's take this dx interval out of there. And let's go back and looking at the y-axis. So now that the independent variable issue is gone, what other things might we want to consider if we're going to revolve around the y-axis? Which way do we think that would be simpler now?
Would both be equally good because we have those two equations?
Let's think about it. So let's try to use y as our independent variable. Which is not going to work for the shell method. So let's go back to the disk method. There's one thing I wanted to highlight here. So if we go around the x-axis and I want to use the shell method, that means I would need to use y as my independent variable. Which means my integral is going to look like this. V is equal to the integral from a to b of 2 pi times the radius with respect to y times the height with respect to y. I think the radius with respect to y is relatively simple. That's just going to be equal to the y value itself. The height with respect to y, that's going to be a little trickier because as y changes inside this interval, your x values are going to contract and expand on either side. So I think setting up the limits for that integral are going to be kind of tricky. And unfortunately, there's not a piece of, kind of catch-all advice I can give to, shell method works here, disk method works here. I kind of just wanted to give a sense for what are the considerations we should make. And one of them is independent variables. How are they set up? How difficult would it be for me to represent the radius and or the height in terms of that variable? Am I going to get into a situation where integrating is just going to be really hard? Like, for example, in the last quiz I gave, there were, like I mentioned, there were some people that took the approach that ultimately ended up with them having to integrate the natural log of x, which is at this point kind of a dead end. So yeah, there are a lot of moving parts, a lot of things to think about, and I will tell you, you get quicker at it the more you kind of you start to build up an intuition when you start making these considerations, and you can kind of expect what things are going to get in your way and what things are going to make this approach easier than that one, things like that. But unfortunately, I know this is not the answer you were looking for, but it all comes with practice. It all comes with experience.
Professor?
Yep.
I have a small doubt. How do you, revolving about the y-axis, like how is it gonna look like? Like I feel like there's gonna be an overlap, right?
There is going to be an overlap, and that's going to be that might be another consideration that we have to make. Let me think about that more. That it's going to kind of look like a bundt cake pan. It's going to have that kind of impression in the middle. Yeah, let me think about that a little bit more.
The x-intercept should be like +2 and +4. I didn't know if you were gonna like solve it, and I was gonna interrupt you. Sorry.
Okay. Is it +2 and +4?
Yeah.
That's bad. Okay. Well, that actually negates your question, Rios, because that's not going to happen now.
Oh yeah, now it's like
Yeah.
it's just.
Yeah. Now it'll be.
But anyways, can we sort of like think about it in this situation? What if it was -2 to -4? 4. How would you sort of like do it? Just out of curiosity.
Let me get back to that, because that was not actually something I intended us to get too deep into.
Okay.
And since I'm going to post these, let me actually make those corrections here. But yeah, I really intended this to be all on one side of the x, or all on one side of the y-axis. Okay. But yeah, now you're not going to get that overlap. You're kind of going to get, now it's really going to look like that bundt cake pan situation where you're going to have that hill along the outside in a circular arrangement with the hole in the middle. Yeah, that overlap would pose some difficulty. Any more questions here? All right, we've been going at it for quite a while, so let's go ahead and take a break. Let's come back at 8:15. Then we got a couple more things to cover, and then I'll let you go for the week. So yeah, let's reconvene at 8:15, and I'll see y'all soon.
Actually, the overlap could be sort of like subtracted, right? Like you just have to take that small fragment outside.
I actually think that you wouldn't even need to integrate the whole thing. So let's say that region, that parabola really did have x-intercepts at -2 and 4. Then really the volume is going to come totally from whatever wherever that parabola is higher.
Uh-huh.
So really you could get that volume just by integrating from 0 to 4.
Okay.
Because the overlap is just going to get absorbed into the rest of the cell.
Oh yeah, that's just gonna get absorbed. Yeah, that's true.
All right, I'm hoping everyone's back. Let's go ahead and get into our next section here, which I'm hoping you can see. Please let me know if you can't. So next thing we're going to be talking about is work. So I'm going to assume that we're not coming in with a strong physics background, but if you are, then a lot of this is going to be a little bit of a rehash for you, but that's okay. So just some preliminary things to think about before we get into the concept of physical work. So a few definitions. So force. Basically, a force is any action that changes the motion of an object. So either causes it to move or either causing the motion of an object that's already moving to change, slow down, stop, could be basically anything. Anything that causes that object to change how it's moving. Usually you can look at this force as a push or a pull. That's a little bit of an oversimplification, but for our purposes and for right now, push or pull is a fine way to look at what a force is. What is displacements? A couple different ways to look at it. Difference between the final position and the initial position of an object. So, and kind of implicit in that is that you have to have some reference position. For example, the origin is a good reference position. You know, if I call the origin 0, then basically however far I am from that in, let's just say I only care about the x direction. So my separation to the right of that would be a positive displacement. My separation to the left of the origin would be a negative displacement. And I'm doing that all in reference to x equals 0. Also a change of position, kind of like I just mentioned. And really, you see this a lot in math, and you're going to continue to see it. That the word change kind of implies that you are comparing to, not similar. I don't want to say similar because that has different connotations, but you know, two states of some objects. So yeah, initial position minus final, or sorry, final position minus initial position. That'll give you a change. So what is work? So those of you who do have some kind of background in physics, you will have seen this before. So work is, the physical definition is some energy transfer to an object by a force, by applying a force to that object and displacing it. So both of those things have to happen. So there has to be an object that I'm A, applying a force to, and B, it has to move. If both of those things don't happen, then work is not being done. The kind of the quintessential non-example is, you know, if I hold this pen right here, you know, it takes a force for me to hold this up because this pen has weight. It requires energy on my part to keep this pen in the air, but it's also not moving. So no work is, I'm not doing any work on this pen at the moment. So both of those things, both of those ideas have to be present, force and a displacement. Mathematically, work is equal to the product of the force and the displacement. So if I multiply those two quantities, the force and the displacement, then I'm getting a value for work. Leave that there for a second. I see some writing. Right, so a little bit of more diving into the physics here. Newton's second law of motion, which is something I'm fairly certain you've all seen in some form, but basically the force on an object, or the total force on an object, is equal to its mass times its acceleration. And I've also included here you know, some more calculus friendly representations of that. So let's talk about derivatives for a little bit. So if I take the derivative of a function, what do you remember about what that tells you of a function? Like what does a derivative give you?
Instantaneous rate of change.
So let me know if this sounds familiar to you. At some point, you probably saw the phrase instantaneous rate of change. And that's really what a derivative, that is why it was developed, that's what its purpose is you've been finding slopes probably since you were a freshman in high school, and a slope requires 2 points. I have to have some change in my independent variable to find that slope. If I have a derivative, I only need 1 point to find that value. So derivative, instantaneous rate of change. This V here, this stands for velocity. So velocity is, the rate of change. It's basically the rate of change of the displacement of an object over time. So the reason I've written this out is acceleration is the rate of change of velocity over time, and velocity is the rate of change of displacement over time, which is usually given by s. So if you kind of stack those things up like that, then acceleration is this. Oh, sorry. Yeah, acceleration is the second derivative of displacement. So we're going to see some of these things as we calculate work using calculus. So how is work expressed, or how are all these different quantities expressed? So if we're looking at SI units, which is what most of the world uses, force is measured in newtons, mass is measured in kilograms, and displacement is measured in meters. So a lot of the calculations, we're going to be doing both the SI units and the imperial units for our calculations, and work is measured in joules. And as we said before, work is calculated by simply multiplying force and displacement. So yeah, a joule is equivalent to a Newton meter. So those are the SI units. In imperial units, force is going to be measured in pounds. Displacement is measured in feet, and so that means work is measured in foot-pounds. You're not going to see there is an imperial unit for mass, but it's not something that's widely used. Usually we just express pounds for any force of gravity we want to think about.
This might be slightly off topic, but like in a professional setting in the US, like how frequently do you actually use imperial units, or do you only use it to like convert to, I don't know. Yeah.
So thinking back to Newton's second law here.
Can you hear us?
If the acceleration of an object is constant, then what other idea is going to be constant? What other quantity has to be constant? Think to Newton's second law of motion.
The slope.
What's
the
related
slope.
to acceleration?
Yeah.
So Newton's second law says that force is equal to mass times acceleration.
Oh yeah, there's no force act. It's a constant force.
So it stands to reason that if acceleration is constant, so I have not been able to hear you. I'm very sorry about that.
Wait, Professor, can you hear me?
Oh my gosh. You know what? I put my speaker on mute. I can hear you now. I am so sorry, everyone.
Wait, did you hear me like when I said the slope and stuff?
No, I only recently started hearing you, so maybe I should pause for a second. I'm very sorry about that, everyone. So were there some questions that I needed to go back and answer? You can definitely take some time to do that.
Someone asked how often do you use imperial units in like in a real life job or something?
I mean, it depends on where that job is. If you're working like if you're working anywhere in the scientific community, you're going to be dealing with metric. But just think about the way we express weights and distances, and really any measurement in the U.S. They're really all imperial, and we're one of only a few countries that kind of sticks with that as our default. But yeah, if you're in if in an engineering field or in the scientific community, it's going to largely be metric, the SI units. All right.
Yeah.
Okay, so I guess did someone answer this question? I just didn't hear it. So if acceleration is constant, then that means that the force on that object is also constant. So this is going to be kind of our simple case here, where if our force is constant, then calculating the work is going to be really, really simple. So like I said, work is equal to force times, and I'll go ahead and put this alternative. Like I said, you'll see displacement sometimes represented as S, but yeah, really force times displacement is going to give you the work. And really that's going to always be true. It's just that when the force is constant, the calculation is really simple. So gravity, since we have a couple different systems of units here, we're going to have a couple different, constant accelerations of gravity. If we're in SI units, you're going to see, and those of you who have already taken some physics and things like that, you've probably seen this constant 9.8 meters per second squared. In imperial, you're going to see 32 feet per second squared.
Wait, exactly 32?
It's not exact, but it's close enough that it's pretty much always expressed exactly as 32. Every once in a while, you'll see the acceleration of gravity as 9.81 meters per second squared. It's really all a matter of how accurate you need to be. Ooh. You good there? So let's actually do some calculations. So the first one we're going to look at has to do with constant force. So I have a book with a mass of 2.5 kilograms. How much work is required to lift it to a shelf 1.6 meters high? So if I'm lifting a book, what force is it that I'm actually having to defeat there, or having to counteract?
force of gravity times distance.
Yeah, force of gravity. So first, let's calculate that force of gravity, and I'll call that F sub g here. So Newton's second law tells us this force is basically equal to the mass times the acceleration. And in particular, is going to be equal to 2.5 kilograms times the acceleration of gravity. Since I've given you a mass in a metric unit, an SI unit, you need to give me the acceleration in the appropriate unit. So I get 2.5 kilograms times 9.8 meters per second squared, which is 24.5 newtons. So I have the force and I have the displacement, so I can pretty easily from there find the work. So work is going to be equal to 24.5 newtons times 1.6 meters, which is equal to 39.2 joules. Any questions there? Okay. All right, so let's do one in imperial now. So how much work is done lifting a 20-pound weight 30 feet off the ground? So I'll let you all drive a little bit. So how should I get started making this calculation?
So it would be 20. Sorry, I missed the imperial units.
Okay.
But yeah, it would just be 20 pounds times 30 feet, wouldn't it?
Right. So I mean, when you're dealing in imperial, like in the imperial system, we don't really deal with mass. We just we just deal directly with weight. So in this case, yeah, we're just looking at, and I'll go ahead and do this more symbolically first. So force of gravity times displacement, which is going to be 20 pounds times 30 feet, which gives us a total work of 600 foot-pounds. So yeah, when you're dealing with constant force, these calculations can be quite trivial. Any questions on either one of the first two so far? All right. So how about variable forces? So now here's how you calculate the work. Obviously, it looks a little more involved. So if I have a variable force, basically what I'm going to be doing is this, and I'll try to draw a graphical representation here. Let's say this axis, my x-axis, this is all displacements. My vertical axis is going to be capital F, representing force. And let's say I have a curve that doesn't really matter what it looks like, some continuous function. And I want to find the work done from x equals a to x equals b. So basically what I'm going to do here, and hopefully this looks familiar to you, I'm going to take a bunch of little subintervals, and for each one of those little subintervals, I'm going to assume a constant force and multiply it by this very small distance to get the work done over that little subinterval. So this little sketch that I'm doing here, what does this remind you of? What other processes does this sort of look like?
Integrating.
Yeah, I mean, I'm still integrating, and even the picture itself kind of looks like I'm finding the area underneath the curve, and that's not a coincidence. So if I'm finding the work of some variable force, then really what I'm doing is I'm taking that variable force, I'm gonna chop that function up and do these really small intervals so I can treat them all as a constant force and find the work that way. Then when I add those all up, I'll have my my total value for work. So this is the integral we're talking about. So really what we're doing here is we're treating this force as the rate of change of our work. And when we have that force, basically we're just accumulating a lot of work over many different subintervals by multiplying the force times this very small change in displacement. And if I do that over the entire interval, then I get work. So any questions there? I want to make sure that we're okay with that before I go too much further, before I do any calculations with variable force. Okay. So let's look at an example here. So I have a particle. So when a particle is located x feet from the origin, a force of x squared plus 2x pounds acts on it. So how much work is required to move the particle from the origin to 5 feet away? So you just put at the top of the slide here, how do we find work? So if this is the integral we're going to use to find work, help me fill in all these missing pieces here. What should our limits of integration be?
Zero to 5.
0 to 5. And how about the integrand? What function are we going to integrate?
X squared plus 2x.
Yep, x squared plus 2x. Any questions on how we set that integral up before we start computing it? All right, let's go ahead and do that. Right, do we agree with 200 foot-pounds? All right, so I want to find the work done here by showing this graph. So I have the graph of a force function in newtons. It increases linearly to so the force increases linearly to some maximum, and then the force remains constant. So how much work is done by the force to move this object 8 meters? So what's a good way to start looking at this? How can we approach this?
I mean, couldn't you just calculate the area up to 4 and then add it to the area from 4 to 8?
That's essentially what we're going to do. So, I mean, really, let's start with, we're going to have to divide this up because really we have two different situations here. So you say find the area, and really that's, yes, it's the area, but really, how are we going to find that area? Like, let's pretend this wasn't a straight line, and I couldn't just rely on my formula for the area of a triangle to get that for me. What should I really be doing? Well, you know, let's call this work 1 and work 2.
Take the integral of the different areas.
Okay, so let's set up the integral for work 1. What should my limits of integration be?
0 to 4.
0 to 4. And then I want to integrate f of x dx. So now we need to represent that straight line in terms of x. What's a good equation for that that straight line from x equals 0 to x equals 4?
Rise over run.
Yep. And just to illustrate it, I'll leave it unreduced at 30 over 4x dx. Which we integrate that comes out to be 30x squared over 8. From 4 to 0. And I believe that comes out to 60 joules. Yep. So that's one piece we need. But what is true about this force over the interval 4, 8?
It's constant.
It's a constant force. So how can we find the work there?
Just multiply the length times the height.
Yep. So yeah, this one, since we have a constant force, we can just treat it as a more simple product. So our force is still constantly 30 newtons. And the distance, I'll just be really explicit about this, is going to be 8 meters minus 4 meters. And that'll be equal to 120 joules. which means the total work is going to be equal to 180 joules. Any questions for this example? All right. So let's talk about Hooke's law. So this is another, if you're going into physics or if you've already taken a semester of it, you've probably seen this. But Hooke's law basically is describes the force acting on elastic objects. So usually you see this applied to springs or any kind of like elastic cord can be modeled using Hooke's law. But basically what Hooke's law says is that the force on, let's just say a spring to simplify, but the force on a spring is proportional to that length that you compress it or that you extend. And that constant proportionality is usually represented by K. You'll also hear it called the stiffness of a spring. Basically, the larger K is, the more force is required to displace a spring, to change its length in either direction. Okay, so let's do a calculation with this one here. So I have a spring which is naturally 10 centimeters long, requires a force of 40 newtons to stretch it to a length of 15 centimeters. So first thing I want to do is how much work is needed to stretch the spring like this? So I know that in general, work is going to be equal to this integral from a to b. The force is a function of x times dx. So in our case here, what is the force on this spring? How can I represent it?
Kx.
Kx, right. So I have this integral from a to b of kx dx. But I don't really know what k is yet. So do we have a way to figure out what k is?
You sort of integrate it, and then whatever you get other than k, you take it to the other side.
Okay, so if I integrate this, which I absolutely can integrate, but I won't be able to really evaluate it because getting a number out of this integral is going to require me to know to have a value for k. But since you brought it up, let's go ahead and start doing that. What is, and I think I have more bullets on this slide, so let's just put them all up here. Yeah, just do them all at once. So if I were to integrate this, first of all, what would the limits of integration be?
$10 to $15. Wait, am I right? I don't know.
Okay, well, let's talk about it. It's like, I was gonna suggest 10 to 15, but let's talk about this. In Hooke's law, we have f of x equals kx. What does the x really stand for? What does it represent?
The displacement of the mass.
So yeah, it's the displacement of the spring. Remember that displacement is in relation to its natural length. So does it make sense when I say the natural length of a spring? Is that clear to everyone? So I'll try to explain it a different way. The natural length of a spring is basically how long is that spring if there's nothing acting on it. Like if I were to just lay it on a table, it's not bearing any weight, it's just at rest. Whatever length that is its natural length. So if this spring is naturally 10 centimeters long, then I'm going to call that x equals 0. And then I'm going to stretch it to 15 centimeters. So I don't want that upper limit to be 15. I want that to be 5. So remember this x right here, this x does not represent length. It represents displacement from natural length. And Hooke's law says kx dx. All right, we okay with this so far? All right, so Ria said we could integrate this now, which we absolutely can. What is the integral of kx?
Half kx squared.
Yeah, so 1/2 kx squared, evaluated from 5 to 0. That's going to give us 25 over 2. Okay. So now, I mean, we've made some headway. We know that the work
Wait,
is equal to
Professor, I have
this.
a doubt. Why is it not 10 and 15? Like, I don't know. I just
So,
feel-
and that all comes from, so our variable is x. And let me back up a little more. I think the first example we did, the displacement was simply, I called that initial position or that kind of baseline position the origin. So really, whatever the x value was the displacement. But in this case, let me try to draw this spring here. Good enough. So like this, let's say this is my spring uncompressed or unstretched, it's at rest. This distance right here is 10 centimeters. So that spring is totally at rest. It's that's its natural length. So that means that I would call this right here x equals 0. Because in this situation, the displacement from its natural length is 0. The spring is at its natural length. It's not displaced from it at all. Does that make sense, or should I take another try at it?
No, I get it.
Okay, good. So, and then, just building on top of that, if I were to extend this out more, then this right here would be x equals 5 centimeters. So yeah, and x is not always purely the difference, some displacement from 0. Really, it's a displacement from whatever the appropriate reference is. In this case, that's 10 centimeters the 10 centimeter length of the spring. So we have our work done on the spring is going to be equal to 25/2K. But it still remains, we got to figure out what K is. So how can we find that stiffness constant of our spring? So let's take a look at Hooke's law here. I know that when X has a value of 5 centimeters, what does that tell me about f of X? What does that equal to? When that displacement is 5 centimeters, what's the force acting on the spring? So hopefully we're thinking it, but it's the force is 40 newtons. This is given to you at the outset here. So from there, I can use that to solve for my my stiffness constant. So 40 newtons equals K times 5 centimeters. And that means K is equal to 8 newtons per centimeter. And if we wanted to, we could have converted this all to meters because that's kind of what we're used to, but actually, maybe we should do that because we're going to eventually express work in joules. So K is equal to 8 newtons per centimeter, which is going to mean it's going to be equal to 800, I believe, newtons per meter. So just to kind of illustrate, here's the conversion factor I'm doing here. So 1 newton per centimeter is going to be equal to 100 newtons per meter. So now that we have that, we already kind of did the integral beforehand, but now we're going to get this 25/2 times 800 newtons per meter.
So are we, just to go back to the top part, when we take the antiderivative, we're only doing that with X and not with K.
Yeah, so, and that's a very good point. K is not a variable. K is a constant. We just don't know what, at the time we did that integral, we did not know its value. But K is a constant. X, on the other hand, I can stretch this spring or compress it to any value of X. X is going to vary. But K is constant. We just didn't know what its value was yet. So because of that, we can make the integral just treating K as a constant. Do we agree with my number of 10,000 joules? Okay. So now that I have that, how about this last question here? How much work is needed to stretch that spring 5 centimeters further.
Oh, that's gonna be 15 and 20, right? Like integration from 15 to 20.
So I don't think it's gonna be 15 to 20. Because I think you're still falling into the same pitfall of
Yeah.
so not 15 to 20, but what should it be?
The 0 to 10 now?
Not 0 to 10 because, and this might be, maybe I didn't word this clearly enough. I want to stretch it 5 more centimeters. So assuming I've already stretched it 5.
So then
Sure.
5 to 10?
5 to 10. And really what I should be doing is, let's convert. I don't think this caused a problem for the way I did this the first time. I'll have to go back and look at it, but let's instead do 0.05 to 0.1. And now we have our value of K.
Sorry, where are you getting 0.5 and 0.1 from?
So let me off to the side here. So X equals basically X1 and X2. This is going to be 5 centimeters or 0.05 meters and 10 centimeters or 0.1 meters. Is that what you're asking?
Yeah, I just didn't make the connection. Thank you.
Yep. Okay. So from there, I said K was equal to 800 newtons per meter. So that 800x dx. And really, I'm going to go ahead and jump forward a little bit because we already did the integral ahead of time. This integral is still going to be 400 x squared. Now we just have to evaluate it at these limits. And I'm sorry to do this to y'all, but I need to go back and do some repair on this very first thing we did. So we really should have converted this. I think we're off by several orders of magnitude. So if we evaluate that from 0.05 squared, should get 1/2 times K times 0.05 squared. So I still believe 800 Newton per meter is still going to be good, but then this work is going to be need to be changed.
I have a quick question. It's not entirely pertaining to this this lecture,
Yeah.
So I'm going through the WebAssign and I noticed that for a lot of them, it starts off relatively nice and easy, and then the last like 3 to 4 questions get super duper like complex.
Yeah.
And I was wondering if the exams are gonna reflect the level of difficulty some of these problems are on WebAssign is happening, or if it's more like the quiz pace.
I'll tell you right now, the quizzes are the exams are going to have things that are on them that are going to be harder than quizzes.
Wait, is it WebAssign or web work?
Well, I think
Web work, my bad.
okay, yeah, it's web work. But yeah, you're going to see things on the homework that push you quite a bit. So my answer to that is, you know, in general, I mean, I'm going to expect you to spend about an hour and a half on the tests, and I expect you to spend quite a bit more time than that on the homeworks. So I will push you a little bit more on the homeworks. Also, you have all the resources in the world available to you for the homework. So yeah, you will see things on the homeworks that are more demanding, more complex than the things I would typically expect from you on a test.
Okay, that's fine. Thank you.
Mhm. So I think for this, I'm getting 0.0025 joules. Whereas for this one, I got 3. So here's what I think I'd like to do. We're right at time. I got 9:08. So what I think I would like to do, I don't want to rush through this one anymore. And there's one more example that I really wanted to look at. I would rather save those for, we'll just do those quickly at the start of class on Tuesday. Yeah, let's go ahead and do that. Does that sound okay? All right. Good. So I apologize for going dark on you guys a while ago. I totally forgot that I had my speakers muted. That won't happen in the future. But yeah, I'll stick around for a couple of minutes if anybody has any questions. Otherwise, I will post this recording tonight. And just a reminder, I haven't seen really anybody show up to talk to me yet, but I do sign on to Zoom at 5:30 every class day for office hours. So if anybody has any questions, please feel free to sign on then. If you have some questions about the homework over the weekend, please email me and I'll get back to you. But just a reminder that that first homework set is due on Tuesday afternoon before class.
Are your office hours only on class day?
Yeah, I mean those are the only times that I have like regular office hours, but you know I am totally open to set appointments with people. So if that doesn't work for you, please reach out to me and I'll work with you. I have flexibility. At present, that's the only time I have set aside every day.
Great, thank you.
Thank you.
Wait, Professor, can we just go through why it's not from 15 and 20 and why it's like 5 to 10 or
Right. So and that all comes from, so I think that our real problem is here, let's define these variables. So what X refers to is, actually, let me word it a different way because I already said this. The difference from 0.1 meters in length of spring. Because let's just think about what's happening when X is equal to or when the spring is 0.1 meters long. If the spring is 0.1 meters long, there is 0 force acting on it because it's not compressed and it's not extended. So I'm only going to get a force if the spring is shorter than 0.1 meters or longer than 0.1 meters. And because of that, I'm not going to have, if I have no force, I have no work.
Thank you.
I just have a little bit more about the homework because I was going to join office hours today. I plan on joining office hours probably at least once or twice a week. I just I took the gym over office hours. So so I'm going